Hello there, Mr. Sutton here, bringing you the BC Calculus Chapter 7 Quiz 1 Review Solutions on Maclaurin series. On this problem, they want the first four terms in general term of a power series to represent this function. So you could treat this as one of those Maclaurin series. This is really a 1 over 1 minus x situation that you could transform if you plug in 5x for x and multiply the whole thing by 2. But another way to do it, probably easier, is just to treat this as a geometric series. So this is just your infinite geometric sum formula in disguise. This top thing here is your A1. That's your first term of your geometric series. And whatever's being subtracted from 1 in the denominator, that's your R value. So that would be negative 5x in this case, because you're subtracting negative 5x to have 1 plus 5x. And now to write the series out, we just start with A1, 2 namely, and then just keep multiplying by negative 5x. So our next term then is going to be 2 times negative 5x, which is negative 10x. And then we have negative 10x times another 5x, giving us 50x squared. Multiply that by negative 5x again. We've got negative 250x cubed. And we've got the first four terms now. We also need the general term. So for the general term, you just need the pattern that you plug in whatever term number you want, and it gives you that term. So we notice there's some alternating of positive and negative going on. So I'm going to want a negative 1 to the n power in my general term, so I can keep flipping back and forth. I also keep multiplying by 5, so maybe a 5 to the n. We've also got a 2 that gets carried through, so just 2 without any kind of exponent. And finally, we need x to keep going up each term, so let me do x to the n. So I'm not really sure if I've got the right general term, but I'm going to write this out. We got negative 1 to the n, 2, 5 to the n, x to the n. And now I'm actually going to go back and check this to make sure I get my series. So the first thing I'm going to have to plug in, if I want this to be positive, I'm going to have to plug 0 in for n. We don't have to tell people what we're plugging in beforehand. We just need some number that works. So if I plug 0 in for all the n's, this is going to be 1. I'm going to have a 2. This is 1. This is 1. So I end up with the 2 that I really should be starting with. If I plug in a 1 for n now, this will be a negative. Check. We've got a 2 times 5, which is 10. Good. X to the 1 is x. Good. And let me just do one more. Second power makes this positive. This is going to be 2 times 25, which is 50. And then we have x squared. So we're good. On this problem, given this f of x that's defined with a sigma expression, we want the first four non-zero terms in general term of a power series for f prime of x. Now, although they didn't ask for the first four non-zero terms of f of x, we're going to write them anyway, just so I can actually have something to take the derivative of. I mean, I guess I could take the derivative of this expression and then write out the series. That's another way to do it. But I like writing out the original series and then differentiating. Okay, so I'm going to start by plugging in 0 for n. That'll just give me 1 times 1, which is just 1. Plug in 1 for n now. This is going to be negative x minus 3 to the first. Plug in 2, now it's positive x minus 3 squared. Plug in 3, we've got negative again, x minus 3 cubed. And although they said the first four non-zero terms, because I'm about to take the derivative of this stuff, I know when I take the derivative, this 1 is going to get zeroed out. So I'm actually going to need one more term in the original so that I have enough for the derivative. So the next term then would be plugging in 4. That would be plus x minus 3 to the fourth. And then let me write the general term of this. So that's actually just going to be the summand if they already gave you the sigma expression. So there we go. All right, so taking the derivative now, 1 again, that's getting zeroed out. And we're taking the derivative of negative x minus negative 3. So that's just going to be negative 1 for this first term. For the next one, I'm just going to use my power rule and keep the parentheses around. So this is going to be 2 parentheses x minus 3. Next, we have minus 3 x minus 3 squared plus 4 x minus 3 to the third. And now for the general term, we'll multiply by this n, which is a constant. So this is going to be n times negative 1 to the n, and then we have x minus 3 to the n minus 1. For this problem, given this f of x here, they want the first four non-zero terms in general term of a power series for the integral of f. Okay, so let's write out the original series. Since I'm integrating, I'm just going to need four terms. if I were differentiating, I would probably need 5, but integrating, you don't get anything zeroed out. So let's just do 4 terms for this thing. So first term is just plugging in 0 for n. That's just going to be 1 times 1, which is 1. After that, plugging in 1, we're going to have 5x. Plugging in 2, we've got 5 squared, or 25x squared. And then finally, we're going to have 125 x to the third. Okay. Now for the general term, that's actually just going to be the summand of my sigma here. So 5 to the n, x to the n, gives me all the terms of the series. And now to take the antiderivative, the integral of this. Now normally when I integrate this, I would need to integrate it in terms of t and put a bunch of t's in an evaluation box, plug in x, plug in 0, and subtract. But when I plug in 0, all these things are going to have a t or an x in them. So if I plug in 0, everything's going to get zeroed out for that back end of the fundamental theorem. So I'm really just going to skip to the part where I plug in x to the antiderivatives of all these things. So my first term then is just going to be x. This was t with an x plugged in, and we don't worry about minus 0. Next, we're going to have, let's see, this is x squared, so 5 over 2x squared, followed by 25 over 3x to the third, and then 125 over 4x to the fourth. And then finally, for this one, 5 to the n is a constant, so we'll just leave that where it is. We have to bump this exponent here up to an n plus 1 and divide by that. So I've got 5 to the n over n plus 1 times x to the n plus 1. And we'll call it a day on this one. For this problem, we have a function f with derivatives of all orders, basically saying, hey, you can make a series out of this. And for all real numbers, with our f of 0 is 8, we have the first derivative, the second derivative, the third derivative, all of this information at 0. They want us to use a third-degree Taylor polynomial about x equals 0, so a Maclaurin series, in other words, to approximate f of 0.3. So our general Maclaurin nth term formula, you're going to have the nth derivative times x to the n over n factorial, and that's the nth derivative of whatever your center is, which is 0 for Maclaurin series. So specifically, our series is going to begin with just f of 0, and then we have f prime of 0 times x, f double prime of 0 over 2 factorial times x squared, and then f triple prime of 0 over 3 factorial times x cubed. Plugging in specific things now, I can say p sub 3, that's my third degree Taylor polynomial, is going to be f of 0, which we said up here was 8, so I have 8, plus f prime of 0, that's 14 with an x next to it, plus f double prime of 0, well that's negative 7, but now we have to divide by 2 factorial, and then we still have, we have this x squared up here. And then finally for triple prime of 0, that's 2, but again we have a 3 factorial we can't forget about down here, and we have an x cubed. For my next step, they wanted me to approximate f of 0.3, so I'm going to write f of 0.3 is approximately equal to p sub 3 of 0.3. And now all I have to do is just plug this in the calculator. So I've entered this polynomial expression as my y1. I like doing that just in case I mess something up. It's easy to go back and fix one thing. And let me exit out of there now, do alpha trace, pull up y1, and I'm just plugging 0.3 into it, nothing else fancy. That comes out to exactly 11.894. For this problem, we have a fourth degree Taylor polynomial for some function given by this p of x function over here. And this is about 0, so it's a Maclaurin function, Maclaurin polynomial. Based off of this, we want to know what the fourth derivative of the original function is at 0. So the key here is recognizing that when you have a Taylor polynomial about x equals some number, you have pretty much perfect information about the function at that number, at least as far as the polynomial goes. All of the derivatives are built into this function here, at least up to the fourth derivative because we have fourth power. So in general, the coefficient of x to the fourth, and this is where we're actually going to figure out our fourth derivative, coefficient of x to the fourth in a Maclaurin series has the form of the fourth derivative at 0 over 4 factorial. This is what all x to the fourth coefficients look like for a Maclaurin series, every last one of them. Now in this specific series, the coefficient of x to the fourth happens to be 1/2. So we're going to set this equal to 1/2. Now to solve for the fourth derivative, all we have to do is just multiply by 4 factorial. 4 factorial we know is really just 4 times 3 times 2 times 1. So that's 24 over 2, which gives us a value of 12. On this problem, we're given p of x, the fourth degree Taylor polynomial for some function about 0. And yes, we already saw this one on number 6. I'm recycling. We want to know if the graph of f has a local max, min, or neither at x equals 0. So in order to figure out the whole max, min, neither thing, there's really only 2 tests we have, the first derivative test and the second derivative test. The first derivative test only requires the first derivative, but it requires some sign analysis, which requires us to know a little bit more about what this function is doing for f prime. But we don't really know what this function is doing at any x value other than 0. So we wouldn't really be able to do sign analysis on this thing to figure it out. The other derivative test is our second derivative test, and this one's kind of special because you need the first derivative still, but the only other thing you need is the second derivative at the same exact point. So we're going to go ahead and use the second derivative test because we can get that information out of this. So we have to start by finding the first derivative to see if this has a critical value. So the first derivative is going to be right next to the x, but I don't have a linear term in this polynomial. Well, no linear term must mean we have 0 times x, which means our first derivative, f prime of 0, must also be 0. So that means that we have a critical value of f at x equals 0. But that doesn't mean it has to be a min or a max. It could be neither still. So to figure out which it is, we need the second derivative to look at the concavity. My second derivative is part of the x squared coefficient. In general, the coefficient of x squared in one of these is going to be f double prime of 0 over 2 factorial. Well, in this particular polynomial, the x squared coefficient is -3. So we're going to set this equal to -3. And then if I multiply by 2 factorial, which is really just 2, solving for f double prime of 0 gives me -6 for that value. Now the important thing out of this is that -6 is negative, which means f is going to be concave down at x equals 0. Well, if I have a critical value, so this is a smooth turnaround basically, and we're concave down with a frown, that means we're at the top of that frown, which means we have a local max. All you really needed right here was therefore f has a local max at x equals 0. For this problem, we want the first 4 non-zero terms of a Maclaurin series generated by this function. Well, option 1 would be to construct this from scratch by plugging in 0 and then taking the first, second, and third derivatives and possibly a fourth derivative of 0, depending on where things shake out. But every derivative you take makes this thing nastier and nastier. So we're going to do it a different way, which is to take the Maclaurin series for e to the x and cosine of x and keep transforming those until we get what we see here. So let's start with e to the x because we're supposed to have this one memorized. This is 1 plus x squared over 2 factorial. Yeah, there's a pattern here. X cubed over 3 factorial. And I'm not really sure how many of these I'm going to need when all is said and done, but I'm just going to start with 4, and I can always add a few more if I need them. So now I'm going to do e to the negative x squared, and then we'll turn our attention to cosine. So e to the negative x squared, I'm just plugging in negative x squared for all the x's and simplifying. I'm going to simplify as I go here. So I've got 1 minus x squared, and this is going to be negative x squared squared, so x to the 4th over 2 factorial, and that's going to be positive. For this next one, I'm going to have negative x to the 6th power over 3 factorial, and we'll stop there for now. Let's take a look at cosine. The series for cosine begins with 1, and then we're doing minus x squared over 2 factorial plus x to the 4th over 4 factorial, and I'll do one more, minus x to the 6th over 6 factorial. Again, I can always keep going if I really need to. So the next step in this, we have 2x plugged into the cosine function. So things that are plugged in take priority over anything else happening. So I'm going to plug in now 2x for all the x's. I've got 1, and then this is going to be, let's see, 2x, the whole thing squared, so that's 2x times 2x, 4x squared. that we're subtracting. I'm going to leave the 2 factorial down there. I'm not going to bother simplifying. I'll simplify at the end if it really helps me, but I generally don't reduce until I absolutely have to. For this next one now, this is, let's see, 2 to the 4th is going to be 16, so 16x to the 4th over 4 factorial. And then this is going to be, let's see, 2 to the 6th is 64, so minus 64x to the 6th over 6 factorial. Next step, we have an x squared multiplied by cosine of 2x. So I'm just going to multiply all of these terms now by x squared. So this 1 is now an x squared. For this next term, we're just going to, and the rest of them, we're just going to increase the exponent by 2 now. So we have minus 4x to the 4th over 2 factorial, plus 16x to the 6th over 4 factorial, minus 64x to the 8th over 6 factorial. Final step, we need to take this last series here and this series and subtract them. So this is essentially the f of x function that I was trying to find in the first place. So to do this, I'm just going to take a look at my lowest term each time, and I'll see if I have any common terms that I can add together. So this 1 from the e to the negative x squared, there's no constants over here that I need to combine with that. So I'm just going to have 1 as the first term of this series. Next, I have an x squared. That's the next highest term. And I have a negative x squared here. Now keep in mind, all of this stuff is being subtracted. So I have a negative x squared over here as well. So that ends up being negative 2x squared. Next, I have a x to the 4th over 2 factorial over here. And I've got a 4x to the 4th over 2 factorial over here that's being subtracted. Well, since I'm subtracting, but I'm actually subtracting this whole series, this is really 1x to the 4th over 2 factorial plus 4x to the 4th over 2 factorial. That's going to be 5x to the 4th over 2 factorial. We just need one more term now. So we've got this negative x to the 6th over 3 factorial, and I have this 16x to the 6th, but it's over a different denominator. So if I want to add this and this other term together, I'm going to need a common denominator. My common denominator is going to be 4 factorial. 4 factorial really is 3 factorial times 4. It's just 4 times 3 times 2 times 1. So to get a common denominator, I'm just going to multiply this fraction by 4 over 4, giving me negative 4x to the 6 over 4 factorial. So if I have negative 4x to the 6 minus 16x to the 6, that's negative 20x to the 6 over 4 factorial. And these keep going, but I'm not going to keep going. I could also reduce these, but I'm not going to do that either. I'm just calling it quits on this one.